Callie is now based in Strathclyde, I guess, but you have a logo of Durham University, so probably you're going to tell us about some joint work with Durham. And the title of Callie's seminar is Collective Dynamics of Quantum Degenerate Cesium. Oh my God, what is that?
Ytterbium.
Ytterbium mixtures. Well, clearly I'm not an experimentalist. So Callie, the audience is all yours, please.
All right, thank you very much, Davide, and apologies for the technical glitch just now. So yes, as Davide pointed out, I am now residing at the University of Strathclyde, but I'm going to be speaking today about some work that I recently finished up with Simon Cornish's group at Durham University, working on his cesium-ytterbium cold atom experiment. And actually, I'm pleased to announce that the paper for this work was just published in PhysRev Research today. So I'll throw up the reference later on in the talk. So just to first acknowledge the team that I've been working with. So this is the cesium-ytterbium team is located at Durham University. Simon Cornish is the PI. Alex Guttridge and Jack Segal helped with a lot of this work, and just recently Tobias Franzen has joined the experiment from Dusseldorf. And of course, our work would be much less complete without the collaboration of some excellent theorists, both Jeremy Hudson's group, who worked a lot on the scattering part of the problem, and then also the group at Newcastle, who did a lot of the work for the collective dynamics part of the paper. So first off, why might we be interested in quantum mixtures, in making mixtures of ultra cold atoms? And the primary advantage of these systems is that they're extremely tunable. So you can tune the interspecies interactions in a lot of these systems, or you can tune one of the interaction associated with one of the atoms in terms of their scattering length, usually with a magnetic field near a Feshbach resonance. And so this gives us a lot of control over the dynamics of the system. So for example, you might look at mean field instabilities, where you're tuning the system from being miscible to immiscible. This first example here is with 85 rubidium and 87 rubidium, where they tune the 85 scattering length. This has also been done with two different species of atoms, such as sodium and rubidium, which is shown down here as they scan the interspecies scattering length. The system goes from being immiscible to miscible. Probably of particular interest to the group here, you can look at counterflow turbulence in a binary superfluid, or at interactions between vortices in two different systems. And then recently, and actually, if any of you were at the talk 2 weeks ago, you might remember this, talking about beyond mean field interactions in these systems, and where we can start to look actually at the role of quantum fluctuations. So I think the talk 2 weeks ago really concentrated on looking at this type of physics in dipolar BECs, where you're balancing, we're using the dipolar interaction to kind of tune and take the net mean field to 0. But you can also do this in a mixture of two different species, or a spin mixture, or two different species of atoms. So this has been demonstrated in potassium spin mixtures, where you essentially tune the interspecies interaction so that the net mean field is very, very small. And then you get beyond, you essentially allow the beyond mean field effects to play a much larger role in the system dynamics. And you can actually drive the system, move the system into a regime where you start to see these bound states that people have referred to as quantum droplets. And essentially in this situation, you have where it would normally collapse because you have a small negative mean field interaction, you now have beyond mean field effects quantum fluctuations that stabilize against collapse. And the result is this really interesting self-bound state that lets us get at some deeper physics than sort of the first order mean field. And this has now been explored in both spin mixtures and sodium rubidium, and also rubidium potassium as well. And then just as a teaser, I won't talk a lot about this in this particular talk, but one of the other roles reasons why one might want to look at quantum mixtures is that this lets you have high phase space densities. So if you want to make ultra cold molecules, so molecules in the ground state, often what you'll do is start with two clouds of ultra cold atoms that are overlapped, and then essentially drive them into a molecular state, and then cool them down and then into the ground state. And cesium and ytterbium are particularly interesting for this because you can make double sigma molecules where they actually have both electric and magnetic dipole moments, which lets you access real spin lattice physics. But that's more of a teaser and less relevant to the physics of today's talk. So in general, why do we like, from an experimentalist perspective, why do we like cesium and ytterbium? Cesium, it's a very tunable system. It's got a lot of options. So we have an alkali atom with one valence electron that has a really rich Feshbach structure, which means that we can tune the cesium scattering properties quite easily. It's a broad resonance, so we have lots of control over this interaction experimentally. And then with ytterbium, we have a lot of different options for making mixtures. So we have 7 different isotopes, two fermionic, 5 bosonic. It's an alkaline earth-like atom, so it has 2 valence electrons. It has a very different atomic structure from cesium, and this means that this actually gives us ways to probe the 2 species independently. So for instance, ytterbium doesn't have it's not affected by magnetic fields in its ground state. And so that means that I can tune the cesium scattering length with the magnetic field and have no effect on the ytterbium except through sort of their interspecies interaction. On the other hand, they have very different responses to laser light fields, different polarizabilities. So I can actually have cesium blind optical potential. So I could stir the ytterbium, make a vortex dipole in the ytterbium and not perturb the cesium at all. So it has some pretty interesting aspects in that regard. That was actually like a whole PhD worth of work before I got to the lab to figure out what all of these interspecies scattering lengths are. So they were measured using 2-photon photoassociation spectroscopy, and then combined with a model that Jeremy Hudson and Matthew Fry had put together to back out what all these scattering lengths were. And in particular, relevance here, cesium and 174 ytterbium have a negative interspecies interaction. So that can allow you to cancel out mean field effects in that system. And then cesium and 170 ytterbium have a positive interspecies interaction, a repulsive interaction, which allows for studies of miscible and miscible dynamics. So thus far, we've been able to make attractive mixtures with cesium 170 and 174 ytterbium, and repulsive mixtures with cesium and 170 ytterbium. You might notice that they look a little strange, or rather the geometries are a little peculiar, and that has mostly to do with some experimental constraints that we're working on. But it does affect the dynamics that I'll be talking about. So just to give you a brief overview of what this type of experiment looks like. Because, as I said, these are very different atoms, we need a whole array of lasers from the nearly UV at 399 nanometers for imaging ytterbium to sort of the far IR 1090 nanometers for making an optical trap. But we basically start out with very hot cesium and terbium atoms. We cool them down using a Zeeman slower. We're basically just using a magnetic field to keep the, make it so the atoms are always absorbing photons from a beam of light that's traveling against the motion of the atoms. Then we catch them in a magneto-optical trap in our science chamber. And from there we do our optical cooling. And this is just zeroing in on the particular laser beams that are relevant for the final stages of cooling the atoms. So as I mentioned, the atoms have very different polarizabilities, and this poses a pretty big experimental challenge because you have to figure out how to make a trap that is that will allow you to cool cesium all the way to degeneracy without boiling away all your ytterbium. And so the way we do this is to use a bichromatic optical dipole trap where we have a 532 nanometer laser overlaid with a 1070 nanometer laser. And these two have opposite sign polarizabilities for cesium and the same sign polarizability for ytterbium, so that you can essentially, by tuning the ratio of the powers, you can tune the relative trap depths for the two species. And this is particularly useful because we basically use sympathetic cooling. So we cool the ytterbium and then we use that to cool the cesium. And so the end result is that we end up with 2-component approximately pure BECs containing about 5 times 10 to the 4, 174 ytterbium atoms and 5 times 10 to the 3 cesium atoms. And you could probably play around a bit and fine tune those atom numbers a bit more, but that's what we settled on. And as I was pointing out, that the trap is a little bit strange. So you have a sort of cigar-shaped ytterbium BEC and a more disc-shaped cesium BEC sitting inside it. So just in to look at this sympathetic cooling in a little bit more detail, essentially what we do is first we load and evaporate ytterbium. So we get ytterbium almost to degeneracy, and then we add the cesium atoms and go through the various stages of cesium cooling, at which point the two samples are overlapped, and we then continue to cool the ytterbium atoms by reducing the trap depth, and the cesium atoms are sympathetically cooled. And it's relatively efficient for cesium. So I think this line shows gamma of about 6. It's less efficient for ytterbium. So once we have a dual species BEC, the first thing most people want to do is give it a kick and see what happens. So that's what we did. And I should say that so this is the paper that's just come out in Fibs Research today. And I should note that Gary Liu over at Newcastle did a lot of this simulations here to go along with this experiment. So essentially what we're doing is investigating the center of mass dynamics of the attractive mixture. So we do this by displacing cesium. And as I mentioned before, we can do that without displacing ytterbium because ytterbium doesn't respond to magnetic fields. So we displace the cesium trap and then let it go. The ytterbium gets displaced just slightly, but that's because of the interactive interaction between the two of them. And so essentially what we have is an oscillating cesium BEC within the ytterbium. And then because it's an attractive interaction, we have a small central ytterbium bulge that tracks the cesium BEC. And so if we look at the center of mass dynamics after a time of flight, what we see is that if we don't have ytterbium, we have very nice simple harmonic motion and very little damping. On the other hand, if we add the ytterbium into our system, we notice two things. The first is that we get a bit of an upshift in the frequency of the cesium, and then we see a significant amount of damping. And this is reproduced quite well by the numerics. So first, if we think about why there should be a frequency upshift, this we can think about just in terms of our GPE equations and our an Thomas-Fermi type approximation. So if we have our coupled Gross-Pitaevskii equations, we should focus on this term here, which is essentially giving us the effect that's what cesium feels because the terbium is there. And if we assume sort of a Thomas-Fermi distribution for the terbium atoms, that turns out to be an additional quadratic potential that cesium feels. And it ends up essentially, when you add in that additional quadratic potential, you see about a 5% upshift, which is what we observe experimentally. So the upshift is pretty reasonable. The damping, on the other hand, requires looking a bit further. So just so you have the right picture in your heads, I'll show you one of video that Gary put together. Start about there, I think. So to start with, we've offset the cesium slightly, and you can see the little bit of a bulge of a terbium that's followed along. And then we let it go. And initially, you just get a nice up and down motion, and then things very quickly start to degenerate into all sorts of excitations. So the numerics allow us to look at what's going on here from an energy perspective. So the gray bar here shows the region that we were able to access experimentally. And you can see that that's sort of where the dominant dynamics of the system occur. There's some interesting beating that occurs at late times, which I'll talk about in a minute. But just looking at the initial sort of 22 milliseconds of dynamics, we see first that we have a net loss of about 85% of the initial cesium energy that's transferred to the ytterbium. And this is through low-lying excitations. And this happens sort of in both the Z and the Y directions. So first you get coupling to the ytterbium Z. And then because those two frequencies, trap frequencies, are actually fairly similar, you get some cross coupling into the y-axis of ytterbium as well. And you can see there's sort of a bit of an out of phase interaction here. And eventually that just settles down into approximately equal components. The Z, or the x-axis, the time scale for anything going on the x-axis of ytterbium is much longer than the rest of the system. That's about 10. That trap frequency is about 10 hertz, so it's quite weak. So in terms of what's actually going on here, I find it particularly useful to look at the velocity profile. And so this is the velocity profile along the Z direction of cesium in the upper plot and ytterbium in the lower plot. And this is again calculated from the numerics. And so we can see that for the first sort of half cesium oscillation, it undergoes coherent harmonic motion. So it's basically acting as a perturbing attractive barrier, which is traveling through the cesium BC and dragging along this central bulge in ytterbium. You can think of it kind of like what might happen when you have an optical potential going through a BC. And then you're going to end up nucleating all sorts of excitations. In our case, this would be an attractive potential, which you don't see as much in experiments. Wait, sorry, there we go. But about after about a half cycle of cesium, it starts going in the opposite direction. The ytterbium is still moving downwards. And so you end up with counterflow in your system. And not only do we have a couple different things going on. One is just sort of straight up counterflow because ytterbium and cesium have different trap frequencies and they have different center of mass oscillation frequencies. But you also have this central bulge of ytterbium that's trying to track the cesium. And so you end up with sort of counterflow, different modes of motion within the ytterbium as well, which come into play later on when we start to think about what the beating might be coming from. So this is more analogous to the type of behavior you would see in a counterflow experiment, where you have two superfluids that are moving against each other at a speed that's above some critical velocity. So then at very long times in the numerics, we see this beating that shows up, and it turns out to be highly dependent on the atom number ratio. And so it's unlikely, or we may go back and try again, but it's given the sort of shot-to-shot variation of atom number in the experiment, it's unlikely that we would see these type of effects. But they are reasonably pronounced in the numerics. And I should point out that this is a different type of beating than what people have seen in quantum mixtures before. So in previous experiments, beating was observed when you had in a system with repulsive interactions, where you have two species that are in that have similar trapping frequencies. And so then it's very similar to having two coupled oscillators. And eventually you expect to see some beating between those two modes. In this system, we have very different trap frequencies for cesium and ytterbium. And the beating, the mode splitting that we observe, has to do more with the dynamics that are going on within the ytterbium BEC, where it actually has these sort of co and counter moving components that either move with the cesium or against the cesium. So what we have here in the left-right corner, this plot is a Fourier transform of the center of mass motion of cesium and ytterbium. The dashed light blue and dashed pink lines show what would happen if you keep one component static. So if I don't move, if at every time step you reset the ytterbium BC to its initial condition and look at what cesium's doing within it. And we see in that scenario, you don't get any splitting or beating. What you do see is that sort of 5% upshift that you would expect from your Thomas Fermi approximation. If we allow ytterbium to evolve along with the cesium, so essentially if we pay attention to back action into the ytterbium, then we see splitting of this mode. And the splitting of this mode gives approximately the time scale that you would expect given the beating dynamics that are observed. Okay, I think I've got a bit more time here. So once we looked at the center of mass motion, the next thing that we had to look at was more of what happens if we vary the scattering length. And the parameter that we can tune in our particular system is the cesium interaction. So in some of the other experiments, like the sodium rubidium images that I was showing at the very beginning, in that case, you're tuning the interaction between the two species. In our scenario, the cesium-ytterbium interaction is fixed. The ytterbium interaction is fixed. The cesium interaction is the one that we can tune by varying the magnetic field. So you're probably all familiar with the Bogoliubov modes and the Bogoliubov energy spectrum that you would expect from a single component BEC. So we're essentially just looking at what happens if we have plane wave excitations on our superfluid background. And we end up with an energy spectrum that has that's associated with sort of sound waves and then also with higher energy modes. And early on, what people looked at was what happens if we tune the if we take an attractive BC and we tune the intraspecies interaction so that it actually so that it can no longer be supported by the kinetic energy associated with the harmonic trap. And in that scenario, what you see is that the wave function collapses, and that the BEC collapses, and then you have a lot of atom loss because you have this very high density cloud of atoms. So you can see something similar in a two-component BEC. Only now what matters is not so much the sort of the trap and the intraspecies interaction. What matters now is the balance between the inter and intraspecies interaction. So I've cheated here and I've just let the masses and interactions all be the same, but it's fairly similar for a cesium and a terbium. The masses aren't that different. And so now we end up with two spectrum, one for density and one for spin. And the one that's particularly relevant here is the density energy spectrum. And because that's the one that leads to our collapse. So when we have the criterion where the net mean field interaction is below 0, then we end up with these imaginary density modes, and we have an instability that ultimately drives collapse in our system. So we can observe this experimentally, and the way that we do this is basically to form a dual BEC at a specific scattering length. We do the same thing every time, and then we ramp the scattering length for cesium to some variable amount, hold there for say 30 milliseconds, and then ramp it back to some constant before we expand and image. And so what we see is that if we have just cesium, so the bottom row of images here, we start to see collapse. We lose the BEC and everything heats up. Once the cesium scattering length is just below 0, which is more or less what we expect given the number of atoms that we have in our experiment. On the other hand, if we have a terbium in our system, then we start to see collapse. We see this distinct change in aspect ratio, and we lose atom number well above the cesium equals 0 scattering length. And Tom Billum did some nice numerics for us. And basically what he did was essentially use all of the experimental parameters, but also include a 3-body loss term for cesium. So when things start to collapse, then the density increases and you should start to lose cesium atoms essentially. And so he matched that cesium 3-body loss and his numerical simulations to our cesium only case here. Sorry. So you end up with very good agreement between numerics and simulation for the cesium only collapse. And then taking those same parameters, he did the same thing for cesium and the terbium. And the big takeaway here is that we actually see a much more shallow transition for cesium plus the terbium than what we see for cesium. And so one of the things that we suspect is going on here is that we might be seeing some of the quantum fluctuation, some enhancement from beyond mean field effects, something related to the quantum droplets that other people have been seeing. And this is an area to look into further once we improve the imaging system, so we get a bit more resolution. So as I mentioned earlier, that one of the things that's intriguing about having quantum mixtures is that you can access these beyond mean field regimes. So if we play around with the numbers for cesium and the terbium, we should have a nice regime where we can tune the cesium interactions and access this sort of droplet physics, or what's also referred to as an LHY gas, where you're just in a regime where you don't necessarily have the right parameters to have a self-bound state, but you do have essentially no net mean field interaction, or very little net mean field interaction, which means that most of the dynamics of your system are governed by these the next order or beyond mean field effects. So we do, as I mentioned earlier, we are able to make other quantum mixtures. So cesium and 170 terbium is the other one that we've successfully made thus far. It's also a Bose-Bose mixture, but it has a repulsive interspecies interaction. The process for making it is very similar to cesium and 174 terbium. There's similar same order of magnitude scattering lengths. So the interesting thing that we see here, though, is that so we were working well within what should be the Miskable regime in terms of the cesium scattering length that we chose to look at. But what we see is actually that there's some significant deformation to the cesium cloud in the presence of a terbium. So we're clearly sort of pushing into the immiscible regime, likely due to the fact that we have very different atom numbers, and that we have to start considering the role of our harmonic trap frequencies as well. So I think the sort of first order miscible and miscible phase transition that I showed on the prior slide requires you to be well within the Thomas Fermi regime, which we are likely not in this situation. But we do notice that the cesium deformation is qualitatively dependent on the ytterbium atom number and our cesium scattering length. So if we remove some ytterbium from our system, then we don't see as much of this deformation in the cesium profile. And then just as a sort of teaser of the direction the experiment is going at the moment, one of the next things to focus on is really taking advantage of the fact that cesium and ytterbium are very different atomic species, and that you can make optical potentials that cesium can't see. And this allows you to do things like look at have cesium and ytterbium in two very different geometries, some mixed dimensions, or as I was saying earlier, engineer a scenario where you might add some vortices but you might perturb ytterbium and add some vorticity into the ytterbium, and then look at how that propagates into the cesium, or how it affects the cesium dynamics. So this is the polarizability of ytterbium and cesium right around the cesium doublet that's near 460 nanometers. So this is really pretty blue light in the lab. It goes very nicely with the green lasers as well. And so what we can do is either tune the wavelength of the laser so that we have a balanced potential between cesium and ytterbium. So maybe get rid of some of the peculiar aspects of our experiment that were due to having highly unbalanced traps. Or you can tune it to a regime where you have cesium blind potentials, where the laser really doesn't affect the cesium at all. And so we've mapped this out using capacitive diffraction, which essentially just means you flash the lattice on and look at how many orders how many diffracted orders you end up getting as a function of time, and you can map that back to to what the lattice strength actually is at that particular wavelength. So we've identified where we might have equal lattice depth and some regions where that would be useful for the cesium blind potentials. So in summary, we've created dual degenerate Bose-Bose mixtures of cesium-174 and cesium-170. So we have both attractive and repulsive mixtures that we can work with. And we've explored the collective dynamics of the attractive superfluid mixture. As far as outlook, there are options for species-specific potentials and a tunable optical lattice, quantum droplet physics, and really it's just a really flexible experimental system. So it has a lot of options. And happy to take any questions. Thank you for listening.
Thank you, Callie. Really interesting experimental talk. I'm happy to start the question time. So if you have any question, either unmute yourself or type the question in. I think Samali is probably first. So please go, Samali.
Yes, thank you for a very interesting and easy to follow talk. I have a stupid question to start with. I think in the beginning you said that one of the species cools down faster and let's say better than the other one in the initiation of the system. And so one would think that this means that the initial temperatures are also going to be different of the two species. Do they ever actually equilibrate, or does it make any difference whatsoever?
So let me just find that plot that I had up. So yes, you are correct in remembering that it's much easier to cool a terbium than it is to cool cesium. It turns out cesium has high 3-body loss. And so you really have to you have to manage the density of the cesium sample quite carefully. It's less critical if you're sympathetically cooling it than if you're just trying to make cesium BCs by themselves. But the answer is they should eventually equilibrate. I think it's quite hard to measure temperature once you've crossed or to get an accurate measure of temperature once you've crossed the BEC transition. So we definitely see that they reach similar temperatures. And then I think what happens is the cesium continues to cool a bit further as it's in contact with the ytterbium.
Yeah, okay.
But you should be able to engineer it so that they do reach the same temperature.
Yes, yeah. I mean, this is just out of curiosity. I don't know much about the technicalities in the experiments, so just asking. Then I have about your in your conclusion slide. You mentioned, was it a quantum bubble or something like that? Very briefly. Well, what do you mean by that? Like.
You mean the quantum droplets?
Yes.
Yes. So what I mean by quantum droplet, actually, I'll go up to one of the initial slides here, which I might have taken a bit fast. So the quantum droplet is the name the cold atom community has given to this state where you have a small net mean field interaction that is balanced. So normally it would collapse, but because you have quantum fluctuations in your system, they repel or keep the system from collapsing. And so you end up actually with this self-bound state. So you can remove the trap and it will still form this little droplet of atoms. And so it's maybe easiest to look at in the figure that I've stolen from Dejun Wang's sodium rubidium mixture experiment, where when they've got all of the atom number ratio correct and they've got the scattering length set correctly, even as the mixture falls, so they've removed all trapping potentials, it stays as this nice little confined self-bound cloud. Whereas if you're more towards your normal BC, you would expect to see them both expand as they fall, as they're released from the trap.
Oh, that's very interesting. Because well, a few years ago we were really working hard on trying to find like similar things as what we ended up publishing as, I think we call it a cue ball, but where basically you've got a quasi-particle BEC which is moving and dragging the trap along with the motion, and then like moving for like several millimeters, something like that. But we somehow managed to miss this one, so it's very useful to have someone from the field explaining these things.
You're welcome.
Okay, thanks.
But yeah, this has been well, since about 2018. There's been sort of an increasing number of increasing amount of interest in this particular.
Okay, well, we published the paper in 2018, so maybe
you might have just missed it.
Available, yeah.
So, are there any other questions? Please, Igor. Yes, unmute yourself.
Yeah, thank you. Very stupid question. You pretend you obtain Bose condensation of your atoms in the trap, but cesium is fermion, right?
No, cesium is a boson, and ytterbium we have 2 fermionic options and 2 bosonic options. So the mixtures that I was talking about were Bose-Bose mixtures.
But cesium have 7.5 spin, no?
Let's see here. So the cesium, we work with it in the m equals 3, m sub f equals, now I'm going to forget if it's plus or minus 3. There's only one hyperfine state of cesium where you can actually make a condensate.
Okay, you know better. Another question is, why do you need ytterbium at all?
Well, so originally this particular apparatus was built with the goal of looking at making cold molecules that have a double sigma cold molecules, so that you actually have a magnetic dipole moment in addition to your electric dipole moment. So it was originally designed with, and still has a goal of going towards quantum simulation and lattice physics. However, along the way, we've been playing around with all of the sort of dual BC type physics that you can do with this system. So we don't need ytterbium specifically, but it does happen to be a nice an atom with a lot of options. So often as an experimentalist, you have to guess a bit when you start setting up the experiment, and so you go with what gives you the most options when everything is said and done.
You said it thermalizes a little bit more cesium.
Sorry, say that again.
That ytterbium helps to thermalize, to cool down.
Yes, so ytterbium turns out to be a fairly nice atom to cool. It has nice scattering properties, and it doesn't have a lot of 3-body loss. So you can actually cool ytterbium fairly easily in an optical trap, or just do evaporative cooling of ytterbium without having to do a lot of managing of density or things like that. Cesium, on the other hand, it is a much harder element to cool because of its high 3-body loss. So yes, having the ytterbium there as a coolant does make our lives easier.
Thank you.
You're welcome.
Are there any other questions? Well, maybe I can ask actually 2 questions. So the first one is, can you tell us what is the, well, I don't know if it's correct to say, but the Healy length of the 2 species compared to the size of the cloud? And I'm asking that because I'm trying to understand what are the type of excitations that you had. So if they're mostly phononic or mostly free particles excitation.
I suspect they're mostly phononic excitations. So healing lengths in the, so I don't, sorry, remember off the top of my head what the healing length
Sure.
is, but they tend, in these type of systems, they tend to be on the order of half a micron. And the size of the system is on the order of 10 microns.
Okay.
You're looking at those type of scalings. But yes, I think most of the, or at least most of the treatment that we did is dealing with sound wave type excitations.
I see.
I think Gary has a paper that will be coming out, is currently working on, which looks a lot more at what's going on in the system.
And I was also curious to know if you saw any generation of vortices.
I wish, so that's what I get excited about, but the resolution of our imaging system is not sufficient at the moment. So I think one thing we had talked about and may end up happening is putting a better imaging system in, and then I think you could do some really interesting vortex physics experiments with this system. But at the moment, the resolution, we're pretty much limited to either loss measurements, so looking at scattering properties or collapse, or center of mass type observations.
I see.
So, or heating. Those are sort of the things we can observe at the moment. But
thank you. Are there any other questions for Kelly? Well, if not, I would like to thank Kelly again. Yeah, just remind you, as I was saying in the beginning, that we will take a summer break in August, and we look to start again the webinar series in September. And we're currently looking for speakers. So if you want to be our next speaker, or you want to suggest someone, please do send us an email. Thank you.